life. As of yet, there is only one example we know of, the life we find here on Earth. There is no definitive proof of life anywhere else in the universe. But that does not mean for certain that it's not out there. If there is alien life on planets other than our own, what might they look like? What would be their biology, and what would we see of their civilization? You might think there is no way to predict this. However, believe it or not, even though we have never seen a single alien, we can make educated guesses based in science to help us know what to expect. And it's all thanks to a simple principle: form follows function. I'm Alex McColgan and you're watching Astrum. And although we cannot say with exact certainty what any aliens visiting us might appear like, or how they behave culturally and technologically, today I'm going to share with you some ideas that might mean, if they ever do land on our doorstep, you aren't completely caught off guard. But first, let's talk about why we look the way we do. As you look down at your own body, even if you do not know what all of it does, you are an incredible example of optimization. You likely have 2 hands complete with fingers and opposable thumbs, ideal for grasping tools and performing fiddly, delicate operations. You have a digestive system that is capable of taking in matter, extracting nutrients, and using them to build up or repair yourself. You have legs for locomotion, a brain for thinking, a heart that will, on average, pump 2.5 billion times across your lifetime without breaking. All of these parts of your body perform specific functions and have been honed over millennia to be really good at what they do, even if you don't feel it sometimes. You are an example of form following function. Thanks to natural selection and random mutation, nature is really good at figuring out what works. When Charles Darwin was voyaging through the Galapagos Islands, he noticed that different finches had different shaped beaks. After observing them for a time, Darwin noticed that the finches with larger, more heavy-set beaks ate different types of food than finches with smaller, daintier beaks. In fact, a large beak was ideally suited to breaking open tough seeds or nuts, while the smaller beaks were more suited to getting in nooks and crannies for grabbing insects. This observation was the basis for his well-known theory of evolution. In this theory, thanks to genetic variation and competition, nature is constantly trying out new things to see what works. And there are certain things that give you an edge. Thanks to all the light that was bouncing around from our sun, organisms that evolved to take advantage of this by developing sight had a bigger advantage over organisms that did not. They could find food better, or avoid predators, or generally navigate their environment. So useful is sight that nature did not just come up with it once. We believe the eye evolved independently about 40 times over the course of life on Earth. 40 different species that previously could not see evolved eyes. This is called convergent evolution, and eyes are not the only example of it happening. Bats are not related to birds, and yet both developed wings to fly. And speaking of bats, both bats and dolphins independently evolved echolocation to help them see in environments where light was not so plentiful. Photosynthesis has arisen dozens of times. Koalas have almost identical fingerprints to humans. This happens because there are some selective pressures that are simply universal. Everything that lives needs to gain nutrients, grow, and reproduce. And as a result, like a plant bending its roots around rocks to find softer soil, nature is good at figuring out the best way of getting what it needs. Because of the prevalence of light, eyes are just a good idea. And when something works, nature sometimes comes up with it more than once. This means that on planets that are similar to our own, it's entirely possible that evolution would end up going a similar way. Although hypothetical aliens on other planets might not look exactly like us, they might look surprisingly similar. I always thought that it looked silly that so many aliens in sci-fi films were humanoid, but perhaps this is more than just a way of easing pressure on the film's costume department. Convergent evolution says this might actually happen. If it worked for us, maybe it just works generally. Any alien that made it to the stars would need to have the ability to work tools. So, fingers or something similar would be a likely addition to an alien race. Large heads filled with complex brains for analysis and problem solving would also be a benefit. The human brain is the most complex of any animals on Earth, with 86 billion neurons. It's not so unreasonable that aliens would be the same. Thanks to our brains, it became less important to keep ourselves warm with fur, as we could craft clothes for ourselves, so aliens may not be hairy or thick-skinned if they are intelligent. Of course, this kind of logic might not carry all the way, because life might not arise on a planet that's exactly the same as ours. If there are different selective pressures, different adaptations might occur. For instance, on a planet with low gravity, plants and animals would be able to grow much taller than on Earth. There would be less energy cost to lifting nutrients up through their bodies or pumping blood around if aliens use those kind of systems. While conversely, on a planet with very high gravity, you'd likely see stockier, shorter, heavier built aliens. Their bones would need to be denser to support them in heavier gravity. Or possibly they would be aquatic, as gravity is less of a problem in water. On a planet that is further out from its star than ours, there would be less light, so an alien's eyes might be bigger. Or maybe aliens on such planets would rely on things like echolocation to see what is around them. On planets with elliptical orbits, seasonal temperatures would vary much more wildly. Perhaps on such planets you'd see an increase in the ability to hibernate, or even come back from near death, such as tardigrades, and their incredible ability to return to animation after being in the harshest of environments like the depths of space. Temperature can also affect size, such as, in the depths of our oceans, there occurs deep-sea gigantism, as large bodies can more efficiently be kept warm, while in deserts, small animals have a larger mass to surface area ratio, allowing them to disperse heat more effectively. On a planet with fewer magnetic fields, more bombarded by cosmic radiation, perhaps life would have shorter lifespans, in much the same way as around the heavily irradiated Chernobyl nuclear power plant. Dogs and other short-lived organisms thrive, while longer-lived humans suffer. In each case, form follows function. Life will adapt to suit the conditions it finds itself in. And it doesn't end there. Did you know that this logic can apply to cultures and civilizations too? When the Spanish conquistadors met the Aztecs, there was a significant technological gap, in spite of both groups being humans. Some historians hypothesize that this can be linked to things like the ease at which each group could farm. Intensive crops that require a lot of effort to grow require more of the population to spend their time farming, leaving fewer individuals free for invention and scientific pursuits. There are likely many other factors at play too, but environment is certainly one of them. Prevalence of coal or other fuel sources could spark an industrial revolution. The presence or absence of silicon or rare metals might help or hinder a computer revolution, speeding up or slowing down a civilization's progress. Once an alien race has evolved to the point where it has become intelligent, unless it came into being through some weird mechanism we don't understand, it probably did so through outcompeting its rivals and collecting resources for itself and its offspring. Civilizations made up of such creatures will most likely also have a hunger for space and resources. Whether they gain these things through clever diplomacy or aggression, it is most likely that they will want them. Form follows function. This quest for expansion and seeking more and more energy and resources led Soviet astrophysicist Nikolai Kardashev in 1964 to propose the Kardashev scale for classifying the different kinds of alien civilizations that might exist out there. He grouped civilizations into 3 kinds. Type 1 civilizations can completely utilize the energy available on their planet. We have not quite reached this point as a species, so we are roughly a 0.7 on Kardashev's scale. Type 2 completely utilize the energy available from their star, possibly by building a giant megastructure such as a Dyson sphere to capture and utilize all of its energy output. Type 3 civilizations would be able to utilize the entire energy output of its galaxy. We have seen no evidence of an alien civilization such as this one, which is for the best, as they would likely see us in the same way we see bacteria. Mildly interesting, but otherwise completely beneath their notice. Other scientists since Kardashev have proposed further additions to this scale. Type 4s that use all the energy in the universe. Type 5s that use all the energy in multiple universes. Or even the enigmatic Type Omega, capable of utilizing energy sources beyond even that, perhaps existing outside of time entirely. Such a civilization would essentially be gods. We would have no way of detecting them, because nothing in the universe would exist except in the way they wanted it to, and we would have nothing to compare their existence against. While this may seem like a bleak outlook for humanity, if we ever came across another alien race, under this theory we would almost certainly end up competing for resources in one way or another, or just getting steamrolled by a vastly higher power. There are actually other possibilities for alien development too. After all, not all humans are interested in expanding ever outwards. In fact, with the advent of internet and online cyberspace, more and more human interaction is taking place in virtual spaces. Carl Sagan proposed a model that classifies alien races based on how many unique pieces of information they collectively know. Although much harder for us to detect at a distance, and admittedly hard to measure, this way of gauging advancement does not require an alien race to infinitely expand. An intelligent race that started looking internally, or even one that spent its entire conscious time in some kind of cyberspace, could still learn more and more about itself and the universe as a whole, while taking less and less space within that universe. For the record, Carl Sagan's scale is alphabetic, where we were at about a Type J civilization, as apparently we knew 10 to the power 13 bits of unique information in 1973. While I haven't been able to find out exactly how he worked out that figure, mention in the comments if you know, we are probably further along this scale now, 50 years on. But as a comparison, a Type Z civilization would need to know 10 to the power 31 bits, more information than exists in the whole universe, so it's unlikely that such a race exists, at least not yet. Ultimately, we do not know for sure. Alien life continues to remain elusive, and while it's true that we have not met an alien civilization, it is comforting to know that it's entirely plausible there would be something about them that we could understand or even find relatable. Form follows function. We as humans are the beings that think and gain mastery of our world. Perhaps one day we will meet another race that does the same things we do. Rather than seeing something truly alien, it perhaps will be like looking into a mirror. I'll leave it to you to decide whether that is a comforting thought or not. Intelligent life is an extremely unlikely certainty. It is unlikely because the number of things that have to go right before it can occur is truly mind-boggling. And yet it is a certainty because it did occur right here on Earth with you and me. And once an event has occurred, the odds of that occurrence become 100%, no matter how unlikely it seemed to begin with. As near as we can tell, this was quite unusual. As we look out across the universe, we think we see desolate, lifeless planet after desolate, lifeless planet. Still, given the sheer number of planets that exist, how likely is it that intelligent life sprang up not once, but twice, or even more times? Are we alone in the universe? What are the probabilities? I'm Alex McColgan, and you're watching Astrum. Today we shall have a stab in the dark at solving these mysteries and see what we hit. To begin with though, let's start with a caveat. If we're going to try to figure out what the odds are of intelligent life existing in the universe, we should ask ourselves the question, what do we mean by life? Life on planet Earth comes in many shapes and sizes, from the tallest trees to the smallest microbes, from spindly insects to birds or fish or humans. Our planet is teeming with life. We generally understand what we mean when we say a living thing. We might define it by it moving around or by it growing. Generally speaking, scientists define life as any system that is capable of eating, metabolizing, excreting, breathing, moving, growing, reproducing, and responding to external stimuli. Essentially, they are aware of their surroundings in some way. They seek resources. They take those resources into themselves, and they use them to grow or create more of themselves. And then they get rid of any waste that's left over. Ew. Some forms of life are much more active than others, but even things like plants can move to face the sun, open their buds, or spread out their roots over time. So we look at these things and consider them living. Even on Earth though, there are some systems like viruses that push the boundary of what it means to be a living thing. Viruses are so simple that they lack the ability to reproduce by themselves or to metabolize. Instead, they get cells they infect to do that work for them. Are viruses alive? They certainly have proved devastating to other populations of living things, and we can definitely think of them that way, but it's a debate that still rages on in the scientific community. So, although there are certain qualities that are fairly universal for living things here on Earth, we must be careful about how we go about defining life. For instance, most living things on Earth make use of water to function. It carries important nutrients around our bodies and is so vital for all life on Earth that we consider the absence of water to be a serious red flag if another planet doesn't have it. But if an alien was somehow able to exist by pumping liquid methane through its body instead of water, would that stop it from being a living thing? Probably not. So let's keep an open mind, but roughly let's define life as those things that seek out resources, grow, and reproduce. Whether those creatures are predominantly water, like us, or whether they are made from some other elements, or even pure energy, it doesn't really matter. All we care about is the likelihood of them reaching a level of intelligence where they might be able to talk to us. To get to that level, there are still a number of things that need to go right. To begin with, they would most likely need a star to orbit. As near as we can tell, life cannot exist without energy. They would need a planet that suited them. They would need to compete with other organisms for limited resources, thus encouraging them to adapt and progress. In time, they would need to develop problem-solving skills and intelligence as a way of gaining those resources and outcompeting their rivals. Their civilization would then have to survive without accidentally becoming extinct due to a freak meteor strike, or earthquake, or global freezing. They would also have to not destroy themselves. They would have to invest in technology, and would have to develop a level of technology that allowed them to reach out across the universe. They'd also have to have a desire to talk to any potential neighbors, as opposed to being intensely isolationist. And finally, would have to broadcast a signal out to us for long enough that we would be able to spot them. All of this is by no means certain. However, as was pointed out by astronomer and astrophysicist Frank Drake in the first SETI meetings in 1961, all of this could be used to calculate the probability of us finding alien life. He laid all this out in his famous Drake equation. This may look a little complicated, but it's based on a very clever and logical idea. Using the same logic that says you can figure out how many students are in a school by calculating how many students were inducted into the school at the start of each year, and then multiplying that by the number of years students studied for, Drake reasoned that the way of calculating the number of civilizations in our galaxy, whose electromagnetic emissions are detectable, could be calculated, provided you knew the rates at which those other steps happened. Let's break it down. N is the number we're looking for. How many alien races are out there for us to see or hear? This will give us an idea of the odds of finding them. R star is the rate of formation of stars suitable for the development of intelligent life, in number per year. Not all stars are very suitable for life to develop, as some are too cold or too hot or generally too unstable. We need to know how many are being born that could support life. Fp is the fraction of those stars with planets. Ne is the number of those planets per solar system with atmospheres and material compositions suitable for life. If they're covered with lava or are completely devoid of atmosphere or water, it's unlikely that life could form there based on our own planet's example. Fl is the fraction of how many of those planets that could support life actually do support life. Fi is the fraction of planets for which that life becomes intelligent. Fc is the fraction of times that life advances enough technologically to start sending out signals of their existence. And finally, L is the length of time a civilization exists on average. If you combine all of these elements, you could accurately predict how many alien civilizations we would be able to see up in our sky right now. Of course, you might have noticed a drawback with this equation. Some of these numbers are simply not known by us. But where's the fun in not giving it a go anyway? By inputting the numbers that scientists currently believe to be most likely, and by making a few assumptions of my own along the way, we will attempt to solve the Drake equation. If you think that any of my numbers seem unreasonable, let me know in the comments below. So, with that, let's see how many alien civilizations we might reasonably expect to see out in the night sky. To begin with, we can input our values with reasonable certainty. Scientists looking at the Milky Way galaxy can accurately predict how many stars form every year, as we have many examples to draw from. Depending on who you ask, the number ranges from between 3 and 7. Let's say 5 at a conservative estimate. Fp is easy to solve too. Through recent astronomical observations by the Kepler Space Telescope, it's become apparent that planets are very common in the solar system, with each star on average having one. So let's set this number high as well. Let's say 90%. However, the number that we currently predict is at a suitable distance from their stars, as well as having the ideal mix of elements that would produce life similar to ours, is much lower. Of the 100 billion planets in the solar system, perhaps as few as 300 million fit into this category. Obviously, this does not account for alien life that's significantly different from us, but let's discount them for the moment, as then this would be even harder to predict. This gives us a percentage chance of 0.3%, quite a small chance that one of the planets in a solar system is suitable for life, so 0.003 for Ne. So far, so substantiated by evidence. Here is where things get a little tricky. For the number of times that life has arisen, we only have one example to draw from: life on Earth. To date, we have not proved that life arose on Mars or Ganymede, for all the conjecture on that front. So we can take this estimate one of two ways. As near as we can tell from the fossil record, as soon as the planet cooled down enough, life came into being, which might indicate a high value for F, perhaps as high as a certainty 1. But on the other hand, from what we know, all life originated from a common ancestor, which is to say, life formed on this planet from non-biological matter exactly once, and has never risen up again since. Scientists have looked for evidence of bacteria that might have independently come into being, but so far haven't found any. This may be a coincidence. Perhaps life did arise multiple times, but the life that arose first was more advanced and so outcompeted the newly formed simple bacteria into extinction. Still, it means that life is either incredibly certain or 1,000,000 to 1. Let's go with the more pessimistic number and see where that takes us. Fl equals 0.0001%. We encounter the same problem for the arising of intelligence. There are numerous examples of animals displaying forms of intelligence. Octopi can open jars and solve puzzles, and some birds and apes can use tools or even use sign language. Perhaps this proves that, given enough time, life always evolves into becoming more intelligent. However, if we want to be strict about it, we could also accurately say that all the millions of species that have existed on the Earth, only one was intelligent enough for our purposes: us. Which makes the odds seem very low for it happening. Let's once again input our 1 million to 1 value for Fi, again just to be pessimistic. In terms of how many become technologically advanced enough to start communicating, I think this number is likely much higher. Although we only have one species to compare to again, it's worth noting that humans are unintentionally chatty with the universe, quite by accident. Thanks to industry and transport, we are altering the chemical composition of our atmosphere, which is something an alien race could detect. Certain molecules in our atmosphere are only there because they are man-made. We also send signals out into space thanks to our radio signals and satellites. Sometimes we even send signals out into the stars deliberately, such as the Arecibo message, which was broadcast from Earth in 1974 and contained information about human civilization and history, expressly so any aliens that heard it could learn about us. Although these signals would not travel far on the grand cosmological scale of things before becoming dispersed and indistinguishable from background radiation, we would count as a communicating race. So I'm going to predict this number as high. Let's say 70% of intelligent races reach this level. Finally, how long do civilizations survive? For this number, sadly, we do not even have a single example. We do not know how long our race will survive until we die out, by which point there will be no one left to write down the final figure. However, although there are numerous dangers that could end us as a species, ranging from meteor strikes, nuclear war, or even solar flares, the longer we are able to survive, the more likely it is that we will go on surviving. This is because once humanity spreads out, we become more and more resilient to a species-threatening catastrophe. If we are on multiple planets, a comet hitting Earth would no longer threaten the survival of our species. If we are in multiple solar systems, a solar flare would no longer be able to get all of us. Species could, in theory, reach a sort of immortality level in this way, lasting for potentially billions of years, as long as they could get out of the danger range. Let's be optimistic and use this figure. What does that give us for the Drake equation? Based on these assumptions, our answer is 0 in our galaxy. If civilizations live for trillions of years, which is longer than the universe has existed for, we'd still be at 0 for these values. Given these odds, our chances of ever hearing from another civilization is next to non-existent. But that's just the thing with this kind of estimate. If we instead assumed that life arising was certain, and that intelligence arising was certain too, our final answer for even a 1,000-year civilization would no longer be 0. Instead, that comes to an answer of 9 in our galaxy. 9 intelligent races who might be up in the stars right now trying to communicate with us. And if races routinely do make it to functional immortality to the point where their civilizations last for billions of years, then we would see as many as 9,450,000 in our galaxy, or more. I know these are hypotheticals, but I find this very interesting. Putting the numbers through the equation makes it a bit more tangible, a bit more magical and exciting even. According to the Drake equation, the sky could be completely silent or absolutely teeming with alien life. If it is the former, then we should probably prepare ourselves for a long, lonely existence. We should learn to get along with each other, because we are all the life we are ever going to see. There will be no aliens stopping by to say hello. But if it is the latter, it leads to a very important question. Where are they all? But that is a question we will have to look at in the next video of this series. For now, my own biggest takeaway from this is that we need to try to refine some of these numbers. Through the efforts of rovers like Perseverance on Mars, we are already taking steps towards attempting to find alien life within our own solar system. The more we are able to narrow these numbers down, the more certain we will be as to our odds of finding alien civilizations. Until we find one, it's all a question of odds. And whether the chances are high or low, well, that's very much up to you. So, write in the comments, what do you think? Or what would you rather? Throughout human history, much thought has gone into what alien life might look like. Sometimes they are depicted as grey-skinned humanoids with large eyes, sometimes as strange tentacle monsters. But ultimately, while this is an interesting question to consider, it's not really the most important one. For there is a far more pressing consideration we need to talk about if aliens actually do exist. Namely, if we encounter aliens tomorrow, what might we expect them to do? While this may seem like an idle question, our survival as a species might depend on us knowing the answer. Because if aliens do exist, by the time they find us, it will be too late to consider it. By then, it might be too late to do anything at all. This is a question that determines our species' destruction, or maybe our salvation. I'm Alex McColgan and you're watching Astrum. Join with me today as we see what we should do when approaching the search for alien life. Because depending on the answer to this question, we have some vitally significant choices ahead of us as a species. And seeing as this is a question that scientists and political leaders are not yet considering seriously, let's have a go at it on this platform. For this video, I will draw on some of the ideas and knowledge we've explored so far in the other videos in this series, so if you haven't seen them, then you might want to check them out using the link above. If our speculations on the behavior of hypothetical aliens are to be useful to us, they need to be grounded in real observations as much as possible. For instance, we know that life can arise in the universe, because it did at least once with us. We know that we can see no signs of any other alien life, an idea we have considered with the Fermi Paradox. So any behavior we look at has to line up with this fact. And we have considered how, when species evolve, form follows function. The same evolutionary imperatives that drive us likely would drive other species too. In all probability, everyone needs to eat or reproduce in one way or another, or they would likely all die out. So, although we don't know for certain that alien life is even out there, let's bring these ideas together. In doing so, we gain some revealing insights. To begin with though, let's hold up the mirror to ourselves. We are the only instance of life arising in the universe that we know of. The great human experiment of civilization has been going on for thousands of years and has produced many different types of society: capitalist, socialist, hunter-gatherer, nomadic, and theocratical, to name just a few. If we want to understand the behavior of alien civilizations, we need to consider societies. We thus have quite a few ideas to compare when considering how aliens might behave. Broadly speaking though, let's examine two great extremes and see how they might influence alien civilization. These two extremes are altruism and aggression, love and violence. Let's start with violence. While this may be a pessimistic starting point, it is sadly one we must consider. Because as human civilization has developed throughout eras, different groups of humans have almost always clashed violently. This ties into the evolutionary idea that competition always occurs when there are more organisms than there are resources. Humans are organisms, and we need resources to survive. And so, all too often, war throughout the ages has been fought over resources. Agricultural land, people, and all the labor power and industry they can produce, gold, oil. Even when a civilization develops space travel and reaches for the stars, this issue will still likely exist. After all, we are nearly at the stars ourselves, and there certainly seems to be no shortage of violent conflict amongst us today. So, with a sample size of exactly 1, we have to at least consider the possibility that the other alien races are the same as us, driven by a need for resources to support an ever-growing population. Of course, when it comes to societies, there are even more reasons why clashes might occur. For instance, religious or ideological differences. The Cold War was largely fought between countries that espoused different political ideologies, capitalism and communism, that threatened each other. Alien civilization might equally differ from us ideologically. In fact, it would be surprising if they didn't. And so, it's possible they might feel their ideology is threatened in some way by ours. This could lead to conflict too. This is not even to mention the fact that some cultures idolize violence itself, deeming themselves of worth only when they are winning victories, such as Viking raiders or Spartan hoplites. Others seek to build empires, recognizing it's much easier to take wealth from others than it is to build it yourself. All these reasons are perfectly plausible for an intelligent race that has mastered its planet, outcompeted other life forms there, and likely feels good about doing so. Survival feels good. We enjoy feeling strong. But if this leads to conflict, what might an alien conflict look like? Technology raises the stakes. We currently lack the technology to move objects to other solar systems. Given the vast distances throughout space, unless we intend to just throw insulting messages at each other through the void, actual fighting cannot be achieved until we manage to solve speed of light travel, and probably something faster than that. It is possible that one day we might get around this problem, and this instantly opens a dangerous possibility. It is theoretically impossible to move something up to the speed of light because of the link between mass and energy. The more energy something has, the more mass it has, because the two are linked, and thus the more energy you need to increase its speed further. This is only noticeable at relativistic speeds, but it does mean you'd theoretically need infinite energy to move mass up to the speed of light. But if you throw an asteroid-sized object at a planet at near light speed, then all that energy gets released in one go. This kind of strike can easily wipe out all life on a planet, and the people on it wouldn't even see it coming. Any intelligent race would be very aware of the impact potential of objects such as this. For us, we only need to look at the dinosaurs. You don't need nukes or soldiers on the ground to fight an alien war, just rocks thrown really, really fast. This opens up one possible answer to the Fermi Paradox. If alien civilizations exist, and any of them prove to be willing to do this, maybe the other aliens realized that it was simply safer not to communicate. Letting other races know that you are there would simply place a target on your back. After all, if you could both do this, and they wouldn't see it coming, could they really trust you not to strike first? They could see us as a risk that they are not willing to take. Known as the dark forest theory, this possible answer to the Fermi Paradox says that the only aliens out there are silent simply because they don't wish to be on the possible receiving end of these kind of planet-buster weapons. Like hunters traveling cautiously through a dark forest, they are all either quiet or dead. They have been subject to this selective pressure. However, this is not the only plausible model of behavior that might still prevent us from seeing aliens. The second option is simply indifference. With billions of years of history at play, it might not be the case that we are on technological parity with all the other forms of life that might be out there. Alien life might simply be so far beyond us, they simply regard us as dispassionately as we might an ant. They might not be talking to us because we have nothing interesting to say. Why do you not talk to insects in your garden? The gap is too great. You understand what they want perfectly, and they have no hope of understanding you. Communication would be, frankly, pointless. That said, life might be rare in the universe. If they desire resources and are that far beyond us, they probably wouldn't need to mine our planet specifically. We might have value as a curiosity, something to be left alone to flourish simply because they have decided that we have some value as a specimen in some kind of grand cosmic zoo. And as any zookeeper would tell you, the closer you get an enclosure to look like an animal's natural habitat, the happier that animal normally is. While they might not care about us, perhaps they do not wish to alarm us by stepping into our natural habitat. In fairness, this is a valid line of reasoning. Humanity would likely find it very distressing to learn that we are in fact not at the top of the food chain, and that our very existence depends on the mild indifference of a vastly superior alien race. Of course, if this was true, we would need to be careful. In my home, I was perfectly willing to live and let live when I found ants in my garden. But when ants came into my kitchen, I quickly got out the ant killer. We would do well not to provoke them. Both of these ideas about alien behavior are bleak, so you'll be glad to know that there is one alternative to hatred and indifference. And in fact, it may prove to be the most realistic for higher levels of society: cooperation. Cooperation exists within nature. Not all life competes. Within species, packs of wolves can cooperate to achieve their goals, protecting those within the group even as they attack those outside it. There are giant supercolonies of ants that do this, working together and spanning entire countries, with each hill all considering themselves as part of the same colony. Aggressive to those outside of it, but supportive and even self-sacrificing towards those within. There are advantages to this, as we humans are well aware. We would not have gotten anywhere if we hadn't learned how to work together. Knowledge pooled allows the creation of all kinds of technology. Ironically, no one really knows how to build a computer from scratch, but there are people who know how to build a motherboard, other people who know how to build a screen, and other people that know how to mine the resources. And all these people know that the other people exist, and so can work together. Historically speaking, there is compelling evidence that as time has gone on, we humans have become better at this kind of cooperative thinking too. It used to be that groups of humans were localized into small tribes, fighting other small tribes. However, that elevated to small kingdoms, then big ones, then whole countries and alliances spanning across national borders. Following that to its natural conclusion, at some point, a nation may exist that all humans in the world feel a part of, a unified planet Earth. But why is this a more likely outcome than violence? Simply put, technology forces it. Not only do we remove barriers to communication the more advanced our communication gets, but as our ability to destroy ourselves increases, there simply isn't an alternative except learning how to get along. Other than total annihilation, of course, but that's a pretty unappealing alternative, one would hope. And so, it's possible that aliens develop the same way. If they did, how might they behave towards the universe at large? While they might still be aggressive to outsiders initially, ultimately, they may have attempted to take this to the next level, embracing new alien races as brothers and sisters, part of a great galactic whole. It's just a continuation of the trend. With potentially millions of years of history drilling the dangers of violence into them, they may actually abhor fighting, and there may be millions of aliens of many different races all cooperating peacefully under one banner. Then why don't we see them? Well, perhaps they prefer to let us learn our own historical lessons about the value of cooperation before speaking to us. An aggressive race would not benefit the galactic community as a whole, so until we learn to get along, advanced alien races might not want to share with us their ideas and technology, particularly if such toys could then be used as weapons. Perhaps they believe that we will either figure out how to get along, or else we'll wipe ourselves out. Either way, in the meantime, it is better they stay hands-off. As any parent will tell you, sometimes telling a child something is not enough for a lesson to sink in. Sometimes experience is the only effective teacher. There might be a galactic community out there just waiting to welcome us. Violence, indifference, benevolence. In theory, any of these or all of these in some combination might be the reasons we don't hear from alien life. Ultimately, we would be wise to tread carefully. Meeting alien civilizations might sound exciting, but it would inevitably come with terrible risks. And possibly fantastic rewards. Is it worth the gamble? Looking up to the stars on a bitingly clear night, a horizon away from the nearest town, you'll feel alone. But as your eyes adjust, you are embraced by the light of an entire universe.
surrounded by such scale and wonder, it's hard in that moment to imagine that we are it, isn't it? That we are the only life the universe will ever know, confined as we are on this pale blue dot. Perhaps we are alone. Or maybe, just maybe, given enough time, nature's laws conspire to make life not just probable, but inevitable. I'm Alex McColgan, and you're watching Astrum. Join me today as we explore the chaotic transition from chemistry to biology on our planet, seeking answers to some of the most debated and fervent questions in science. What is life? How could life have emerged on Earth in an environment that would kill us as we are today? And can it begin all over again elsewhere in the universe, or even on our own planet? To begin to answer those questions, let's imagine that while walking across a barren desert, your foot kicks a stone. It wouldn't occur to you that someone put it there or crafted it, since the stone is too simple an object. Now, imagine instead that you stumble across a glistening, precision-made, embossed gold pocket watch. William Paley argued that because, unlike a stone, a watch obviously requires a designer, you'd have to assume that someone had made the watch and placed it there. And because, when you truly think about it, life is far more intricate than a watch, life too must require a designer. It's a compelling argument, isn't it? Even the simplest forms of life are far, far more intricate than a watch, and if a watch requires a designer, surely so must life. Unfortunately, the argument doesn't quite work. But why? What really is the difference between a man-made machine and mankind? Charles Darwin's work on evolution and the origin of species crystallized the idea that life evolves and that all life began from one common ancestor. Therefore, I should infer from analogy that probably all the organic beings which ever have lived on this earth have descended from some one primordial form into which life was first breathed. And there it is, emergence, life from chemistry, something different than the sum of its parts. Darwin understood that life needs no designer. It is able to be more intricate than a watch without a designer because it is a complex, adaptive system driven by natural selection. It has the ability to evolve. A watch is merely complicated. But before we go back 4 billion years to uncover life's genesis on Earth, we should probably all agree on what it is we're looking for. What do you think defines life? What makes something alive? If you're struggling for an answer, don't worry. Even NASA can't get 3 words into their definition without being challenged. This is science at the bleeding edge. NASA defines life as a self-sustaining chemical system capable of Darwinian evolution. Prominent scientists argue that life is not strictly self-sustaining. Life requires an environment with which it has a dynamic relationship, where life draws its energy and raw materials and expels its waste. An environment that is full of free energy, an environment that sustains life. Life's relationship with its environment is crucial to understanding how life is possible. You see, life is, at first glance, in defiance of the second law of thermodynamics. How does the beautiful design of a bacterial cell, with its incredible complexity, control, and order, seemingly defy entropy and emerge out of a structureless chemical soup? According to the second law, entropy should always increase, and systems should get more disordered with time, not less. It was Erwin Schrödinger who realized that it is the environment that picks up the thermodynamic cost in his book, What is Life, in 1944. On closer inspection, when we include the environment that sustains life, entropy does increase overall. The second law of thermodynamics is not broken. In fact, entropy increases faster with life than without. It is this that led Jeremy England, a professor at MIT, to say, "You start with a random clump of atoms, and if you shine a light on it for long enough, it should not be so surprising that you get a plant." Life is incredibly effective at transforming energy and increasing entropy. How effective? Let's compare it to the brightest and most powerful object in the solar system, the Sun. In just 58 microseconds, it produces more energy than our species has in its entire history. Pound for pound though, humans output a staggering 6,000 times more power at rest than the Sun. Despite creating extremely localized order, life degrades free energy to heat, increasing entropy in the universe overall. Unsurprisingly, given that you're watching this video, it's clear that entropy allows for, or even encourages, the development of life. So how did the building blocks of life seemingly defy entropy in constructing order from chaos? How does a living cell build up that can power itself, encode itself with DNA, construct itself too, and have the ability to evolve? And how can it do it all piece by piece while being functional at every step, even though each part is essential? How on earth could life emerge? Well, there is little consensus on the precise way that life actually emerged on Earth, but let's explore the molecules that, without exception, build every single life form on Earth. Perhaps life offers clues to its own origin. The key basic building blocks life uses today, in no particular order, are fatty acids, amino acids, and nucleotides. And all three are believed to have been present on the early Earth, and have even been found on asteroids in our solar system. The first are fatty acids, and despite having little chemical functionality, they create structure and have an extraordinary function built in. These long chain molecules make up cell walls of all life on Earth and are believed to have made the first membranes of protocells. Membranes are barriers and fundamental to create an individual unit. After all, you can't have a house without walls or a country without borders. That's not a political statement. Remarkably, cell-like structures made from fatty acids form spontaneously in water. As anyone who's failed to make a simple mayonnaise will know all too well, oil and water don't like to mix. These fatty acids, with a water-loving head and a water-hating tail, will spontaneously arrange to minimize water's contact with the tail and maximize it with the head. These simple pressures can create a bilayer membrane with a cavity for an early cell to call home. This is called a liposome. Unbelievably, these liposomes can also spontaneously divide and speed up chemical reactions by encapsulating and concentrating the molecules in a smaller space. This is a perfect example how unexpected lifelike behaviors can emerge out of the laws of quantum mechanics. But won't these crude divisions just go wrong and kill the cell more often than not in a hot, salty water? Well, yes, there's a good chance. However, the environment isn't a simple system. It's impure. There are other molecules floating around that can stabilize the cell walls further, like amino acids. A diverse range of these building blocks were present on early Earth and are even present in our solar system. Today, life uses 20 different amino acids to make all the cellular machinery within us, like enzymes and ion channels, as well as larger structures like muscle and hair. There is a miraculous relationship between amino acids that make up proteins and our next building blocks, nucleotides. A relationship that is important in helping us to understand how life's informational system may have emerged. The ability of life to create and store information is achieved by nucleotides, which are present today in RNA and DNA. RNA is believed to be involved in the origin of life because short chains of RNA serve another simpler purpose. They can also catalyze some chemical reactions, which perhaps kick-started life's early chemistry. Nucleotides have other functions too, and feature in several vitally important molecules like ATP and ADP,
the pair of molecules that drive work in a cell,
acetyl coenzyme A, and vitamin B12. In fact, every living cell today relies on what's known as the central dogma. DNA is translated to RNA, which encodes proteins. This is strong evidence that all life on Earth can be traced back to one life form, Luca, the last universal common ancestor. The central dogma is a highly evolved system that has redundancy and error correcting built in. But the ability of RNA to encode proteins may have much simpler beginnings, one that doesn't require enzymes, one driven in part by the same physical pressures as fatty acids forming a cell-like structure, a mechanism that could have introduced information to protocells. You see, different RNA bases can encode specific amino acids. This means that a random string of RNA in early protocells could have produced a non-random string of amino acids, which could have conferred an advantage to the protocell containing it. Perhaps the amino acid stabilized the membrane, and it would have been more likely to survive and divide, potentially reproducing that information and passing it on. So now we have a great primordial soup of molecular potential. We have the thermodynamic encouragement for life, self-dividing cell walls and short RNA strands that could have encoded functional amino acids. How can we get past this primordial soup of small molecules for life to emerge? Well, we also need the one mechanism that is crucial to all theories: selection. Without selection pressures, in 14 billion years, molecular complexity wouldn't have moved much past basic molecules like these, let alone a complex enzyme, because you'd be relying on random processes with very low probabilities. Very much like shaking a bag of Lego bricks together for a few years and expecting a perfectly formed Death Star to pop out. As the size of a molecule grows, the space of possible configurations grows absurdly quickly, and the probability that even one specific molecule can be made in a useful quantity by chance falls to near zero. And that's just for one molecule, let alone a gold pocket watch. The creationists may have a point. Incredibly though, research suggests that the proposed chemical reactions on early Earth were capable of a kind of evolution way before they transitioned to life. Some chemical reaction pathways can produce molecules that catalyze the pathway itself. These are known as autocatalytic. This catalysis increases the flow of resources through one pathway, potentially away from a competing pathway, and therefore increases the first success. When these pathways loop around on themselves, they are known as autocatalytic sets. These are nascent forms of metabolism. Crucially, these metabolisms are spontaneous and can exist without the need for evolved enzymes. We have seen how the molecules present on early Earth interact and produce lifelike behaviors without the need for the highly specialized cellular control. Much of life's chemistry may indeed be spontaneous. Metabolism, chemical selection, division, information transfer, but in order for life to emerge and for all these processes to come together, we need time. But incredibly, not much time at all. The Earth formed around 4.54 billion years ago. The Moon was created 4.5 billion years ago. There were liquid oceans around 4.4 billion years ago, and the earliest life is present potentially as early as 4.3 billion years ago. For something regarded by many as unlikely, it's curious, don't you think, that almost as soon as it is given the chance, life emerges. Maybe life is inevitable. At least it was on the early Earth, because Earth has a lot of free energy and is, in effect, a giant battery. Some 4 billion years ago, our ocean was acidic and lacking in electrons, while the molten mantle just below it was alkaline and rich in electrons. A huge chemical charge imbalance that has been shown to be used to power chemical reactions that are evolving towards life. There is a consensus that somewhere on this world, where the inside of the Earth meets the outside, where the two ends of the battery meet, there was a spark of some sort. There are deep sea hydrothermal vents, gas-filled caves, hot springs, evaporating pools, and volcanic areas totally devoid of oxygen. All have all the elements that we think are required for life to emerge to harvest this free energy source. And all would have killed us if we were able to travel back in seconds. It is proposed that Luca was a methanogen, originating at one location like these. An organism that reacted hydrogen with carbon dioxide to make methane. That's partly why a form of life evolving from scratch now is considered to be impossible because of the oxygen concentration. Add oxygen to hydrogen, and instead of life, you've got rocket fuel. We may never know for sure if a form of life existed before our central dogma ancestral line, but that's not to say life hasn't emerged elsewhere in our galaxy or even our solar system. Planets have been found nearby in our galaxy that are similar to Earth and could replicate the conditions of the early Earth. Our planet is not so special. Given the thermodynamic pressure for the emergence of life, it seems as though life on another planet is an inevitability. There is volcanic activity on moons orbiting Saturn and Jupiter, providing a similar environment beneath the surface to Earth too, which is why scientists are so interested in exploring the icy moons orbiting our nearby planets. Hydrogen-rich volcanic plumes, just like those from our deep-sea vents, have been observed erupting from the surface of Saturn's moon Enceladus. Despite the extreme speed with which life appeared to emerge on Earth, the time to go from single-celled to multi-celled was 1.5 billion years. It's clearly a hard jump in complexity to evolve communication and cooperation between cells, let alone interplanetary communication with alien life forms. So, although we haven't found signs of life elsewhere yet, absence of evidence is not evidence of absence. With all this, looking up to the stars, the way all these molecules work together, it's hard to feel alone in the universe. The early Earth seemed ideal for life to emerge, but then, even if it was less hospitable, there is always a chance. As Dr. Ian Malcolm said in Jurassic Park, life, finds a way.
You may have heard many news stories about all the thousands of exoplanets that have been discovered using the Kepler telescope. As of the 1st of July 2018, Kepler has confirmed the existence of 3,797 planets in 2,841 star systems, with 632 systems having more than one planet. But are any of these planets habitable? What are the chances of life being found outside of Earth? Are we alone in this universe, or can life be more prevalent than we think? And if there is life, where can it be found? I'm Alex McColgan, and you're watching Astrum, and together we will explore known exoplanets in the Milky Way galaxy to see if any of them have the potential to harbour life. Now, we've not been able to actually image exoplanets in any kind of detail. In fact, this is the clearest real image we have of an exoplanet, taken by ESO's Very Large Telescope, which may make you question, if this is the best image of an exoplanet we have, how can we discover exoplanets, and how do we know life could be on one? To answer the first question, we have to look at how Kepler worked. Kepler is a space probe which constantly monitored about 150,000 stars in a fixed field of view using its camera. The field of view focuses on a patch of sky near the constellation Cygnus. This is what Kepler can see. The data it collects is sent to Earth and analysed to see if any stars dim periodically. You see, the concept is, if a star's planet passes in front of Kepler's view, the star will dim. If it dims, for instance once every 100 days, we can confirm that it is a planet and it takes 100 days to orbit. Kepler is really good at finding exoplanets. Before Kepler came into operation, these were the exoplanets we knew about. As you can see, most of them are many times the size of Jupiter. Since Kepler came into operation, we have discovered and confirmed the existence of thousands of exoplanets, with thousands more still unconfirmed. Remember, these are planets which have been discovered in only this patch of sky. There is still a lot more out there. Kepler unfortunately is no longer functioning how it used to, as some of the reaction wheels inside it are broken. However, the good news is that there is a new exoplanet finding spacecraft called TESS, which just came into operation a couple of weeks ago, which will cover an area in the sky 400 times larger than the Kepler mission. It is expected that during its mission it will be able to find more than 20,000 exoplanets. In order to determine details about an exoplanet, the distance from us to its star needs to be worked out using complicated maths. For stars within 400 light years away from us, we can use trigonometry and the orbit of the Earth to create a difference in angles. Beyond that, there is no direct measurement, so the best current method is by comparing a star's color spectrum to its brightness. The color spectrum of a star corresponds to what type of star it is. Once the color spectrum is known, scientists then know how bright the star should be. Comparing the apparent brightness, or the apparent magnitude, to the actual brightness, the absolute magnitude of the star, reveals how far away it is. This method is proven, as scientists have done this test on stars that are within 400 light years, and the results produce similar distances in both tests. Once the distance to the star has been determined, the amount the star dims can be used to see how big the planet is, its distance from the star, and the exoplanet's mass based on the orbit of the exoplanet. Using other telescopes like Hubble, ESO, and eventually the James Webb and the W-FIRST telescopes, these exoplanets can be studied to find out their composition, particularly of their atmospheres. The way this is done is again from the spectra of the exoplanet's light. To give you an example of how this is done, imagine white light shooting through a prism, producing what is actually a blend of colors spanning from violet to red. Light from a star shooting through an atmosphere produces a similar effect, except certain bands of light are not present. This indicates there is a certain gas in the atmosphere that is absorbing the light in that wavelength, not allowing it to pass through. The dips in this image shows what Earth's spectrum looks like as sunlight passes through the atmosphere. The dips show that oxygen is present, as well as water vapor, carbon dioxide and methane. These gases all absorb the sun's light at these wavelengths. Looking at a section of wavelengths and comparing them with other planets in the solar system, sulfur compounds can clearly be seen on Venus, and methane on Neptune is apparent. This means that as we study exoplanets in detail and determine their spectra, we can search for atmospheres that resemble our own. If it does, then the chances are that it could be a habitable world, and also that it may already harbour life. Inhabited planets could have telltale signs of life, like smog and pollution, which would be seen in the planet's spectrum. So, have any exoplanets like these been found? Well, out of the thousands of exoplanets that have been discovered, 16 of them are thought to be rocky planets and sit in the Goldilocks zone, or the habitable zone of their respective stars. Let's just remind ourselves of the ingredients needed for life as we know it. We believe that liquid water needs to be present. Liquid water is essential because biochemical reactions can take place in water. Water is also an excellent solvent that easily dissolves and carries nutrients and other compounds in and out of cells. Life forms on Earth are made primarily of water. In fact, our human bodies are more than 60% water. Life also needs sufficient protection from cosmic and solar radiation, which can break down and damage cells. On Earth, this protection comes from our magnetic field. There also needs to be essential chemicals found in the ground on Earth, and an energy source, which for us is the sun. So the Goldilocks zone is where, assuming other conditions are right, liquid water could theoretically pool on the surface. This zone is always different depending on the parent star and how big and hot it is. Looking at our own solar system, Venus might just be in the Goldilocks zone, as well as Earth and Mars. We already know that only 1 in 3 planets in our own solar system's Goldilocks zone can have liquid water, so just being in the right place is not always enough. The type of star is also important. Our star, although seemingly active on the surface, is actually quite stable compared to a lot of other types of stars. The Sun will likely be 10 billion years old before it burns out. On the other hand, the hottest types of stars will only last for millions of years in comparison. It is thought that this is not enough time for life to form around it, certainly not animal life that can communicate as we understand it. So we have a lot of filters we can now use to narrow down our search for habitable worlds. Out of the original 3,797 confirmed planets, 16 are terrestrial planets that orbit within the Goldilocks zone of their stars. However, the habitable zone of some stars means the planets are close enough to be tidally locked, meaning only one face of the planet sees its star. This proximity to the star also means the planet is exposed to a lot of solar radiation, sometimes thousands of times more than we are exposed to on Earth. In other words, out of those 16, only 4 are likely candidates to be Earth-like, although it is worth mentioning that exoplanets in systems like the TRAPPIST-1 system could still be habitable or have life even if all the planets are tidally locked. But the TRAPPIST system is worthy of its own video, so I won't expand on it here. These 4 exoplanets are Lytton B, Kepler 62f, Kepler 186f, and Kepler 442b. Realistically speaking though, we don't know much about them other than their size and mass. Our current technology isn't accurate enough to determine the composition of their atmospheres. One of the James Webb Space Telescope's missions is to study known exoplanets in greater detail, which is exciting as, in combination with the finding power of the TESS telescope I mentioned earlier, this next decade could be full of discoveries. But by using the Kepler data as a fairly decent sample size, can we estimate how many habitable worlds there could be in our galaxy alone? Ethan Siegel did a very interesting article which I will link to in the description, where out of those 150,000 stars, the chances of seeing anything at all using the transit method is very small, less than 1% for a planet orbiting the distance of Mercury, let alone Neptune, which has a 0.001% chance of detection. This is due to the way planets tend to all orbit along a plane, and if it's not lined up, we won't see anything. Also, smaller planets are much harder to detect. Look how hard it is to see an Earth-sized planet compared to a Jupiter-sized planet. Taking all these things into account, Ethan Siegel placed a low estimate of 6.4 billion planets in their star's habitable zone in our galaxy, the Milky Way. This means at least one of them has to have life too, surely. Well, we really don't know how prevalent life is at all. And until we do some serious research and improve our technology, we have no way of knowing yet. Some people claim that all factors considered, the chances of humans being able to develop and live on Earth was 10 to the power of 10,123 to 1. In other words, extremely unlikely. How many factors actually are needed to be right for life to exist? Is it all over the place, or purely a freak coincidence here? Building on what we know already means the future is going to be very exciting.
A massive thank you to our astronauts on Patreon. This video had no sponsors, but it was still made possible thanks to the hundreds of members we have there. Link is in the description to join our growing community. Patreon is where Astrum truly takes shape, a place for people who love space, who want to see these videos keep improving and reaching more curious minds. Every new member keeps the channel focused on what really matters, making the complexity of space available to everyone. If you enjoy what we do, come join the Astrum community today.